Hello there, class. This is Professor Mike again, and I am going to do electromagnetics with you this semester. So, this is my fourth course with you. I'm sure you are all sick of hearing from me again and again, but I promise you, this is the last thing I'm going to teach you. After this, even if you make it out to NAU, you'll have plenty of other good professors to teach you. So anyway, hope everybody had a good holiday and that you're back on campus, eager and excited to learn new topics. And this one, applied electromagnetics, definitely, or EE 364 as we call it, definitely needs a lot of enthusiasm because the topic by itself isn't the most exciting. It's highly mathematical, and it almost feels like we are doing nothing but mathematics throughout the course. But it is an important topic because many of the ideas that you study here, they apply to all branches of electrical engineering, whether it's communication systems or power, uh, power transmission lines, and so on. So it is a core requirement for an engineering course in any country or any university. So it's not something you can avoid. You have to take it. So let's see if I can make it interesting for you. And if you do your part, as I've always said, if you follow along my lectures, do the homework, also listen carefully and practice the examples and the problems that I do in the class. All this will help you, have a easier time understanding this course and following along than if you just listen to my lectures and didn't quite get down and do the numerical examples and the problems, but you decide 1 week before the quiz, okay, now I'm going to do all of this. That won't be helpful. So as always, uh, please put in the necessary effort, and I think you should be okay. All right, so with that introduction, we can get started. I will follow the same format as in previous classes. That means I will record a lecture, and depending on the topic, I may address some problems in a lecture, or I may have a separate recording just for problems. But either way, the material that I will offer you is lectures, which is basically dependent on my PowerPoint slides, and problems that are either from our textbook, solved in the textbook as an example, or it may be something from the back of the chapter that I solve, my PDF file that I use to solve and present to you. Sometimes I may bring in problems from somewhere else, and if I think those are helpful to you to understand the material. So this is the way we'll do it. One last thing I want to say before we jump in. Compared to previous courses we have done, where we have 12-week session, and each week we have 2 days of classes. Each day you have two sessions, 45 minutes, 45 minutes, and you'll have either Monday, Wednesday, or 2 other days in a week. But in this case, they have told me that it's not 12 weeks, but it'll be a 16 weeks course. But in each week, we only have 1 day per week. And each day, of course, still has two sessions, two 45-minute sessions. but only once a week you have to listen to me. So that only gives me, 16 weeks times 2, 32 lectures, and that I feel is not quite enough, because normally most of our courses I take 12 times 4 or 48 lectures. In this case, we are reduced to 32. So I may have to rush a little bit, which means you have to do more work on your own. That's the way it is. I mean, you don't have to sit in class 2 days a week, but you still may have to do more work during the week to cover for what I cannot cover. Anyway, I'll try to make it as easy as possible given all these constraints on timing. But definitely, as senior students, your workload you can expect to be slightly higher than previously. Of course, I'm always available if you want to send emails, etc. That'll work. Or you can also depend on the co-faculty who have been teaching this course also for many times now, and they are also good resources for you to work with. All right, so with all that, let's get started. I'm on slide 1, which is just the introduction to the PowerPoint and the course. The textbook is Fundamentals of Applied Electromagnetics, Olabi and Ravioli. It's a very popular book in the US. And we'll work with edition 7. So make sure that's the edition you folks are able to get when you go get the textbook. All right, so I will expand this. We're on slide 1, and I will move to slide 2, which lists all the topics. By the way, the syllabus and the plan for the whole course, I have posted that online. I don't want to talk about it because, again, time is a important resource in this course. So I'll let you look through it, but you'll see when the classes are, when their tests are, and so on. So let's quickly jump to the topics in chapter 1. So there is a historical timeline, section 1, then dimensions, nature of electromagnetism, traveling waves, and then there's 3 other topics: electromagnetic spectrum, review of complex numbers, review of phasors. The textbook is an excellent textbook. It's written very well. Lots of nice extra material, plenty of color in the textbook to explain things easily. So please spend time reading the textbook, every page, every word if possible. I won't have time to do that with you. I can only highlight the main points, but I would advise you to spend as much time as possible looking through the textbook. Lots of extra information, and you might find the course exciting if you spend more time with the textbook. So for what I will do, I'm going to skip the entire 1-1. It's again very interesting material in there. It runs to many pages, but I'll leave it to you to go through it. 1, 2, 1, 3, 1, 4 I'll definitely cover in some detail. 1, 5 I may skip. I'll leave it to you to read. 1, 6, 1, 7 is just material we have already studied. Complex numbers, phasors, etc. We did that in electrical circuits 1, electrical circuits 2. So I don't have to spend too much time on those. At least I won't look at any of the theory in the lecture. I may look at 1 or 2 problems just to refresh your memory on these topics. Okay, so that's the plan for chapter 1. Okay, moving on to slide 3. So why study electromagnetics, right? How does it compare to all the stuff that we have already done? And why a new topic at this point? So one way that people and writers of textbooks make the difference between circuit theory, which by now we have studied quite well, all of us, you and I, and electromagnetic theory, right? What are the two ways to look at this, the subject of electrical engineering? So you can say that electric circuit theory, which we are familiar with, it deals with the behavior of devices, R, L, C, transformers, etc., in an abstracted way. So it is abstracted in such a way that the underlying electromagnetic principles do not need to be considered. So circuit theory, we say an R and an L, it depends on some electromagnetics and physics. We touch upon it briefly, but we don't spend too much time there, right? I've always said you've studied all of this, the core principles in physics in high school. So we don't have to go into magnetic flux. We don't have to go into, a dielectric in a capacitor. But we just briefly look at the theory and quickly go into creating models for RLC and mutual inductance and op amps and so on, and we quickly learn how to solve problems using the standard formulas of circuit analysis like KVL, KCL, what are the other laws? Superposition. We also studied about Norton's and Thevenin's equivalent, all that kind of stuff. But there we didn't spend too much time on the basic electromagnetic behavior. So now in electromagnetic theory, we actually get into understanding electromagnetic properties of materials and the geometry in which these materials are arranged. So you have materials, you have steel, iron, copper, non-conducting materials. All of these materials, the properties inside the material that lends itself or that gives a certain electromagnetic behavior. That's what we start looking at, number one. Number two, we also look at the geometry. That means, let's say you take a piece of wire, right? Is it a straight wire or is it coiled? That means, is it many turns? And then does the wire have some iron in it, steel, or is it just by itself? Similarly, if you take a capacitor, right, does it have two flat plates, or is it just a circular, paper? So by looking at the geometry of all these materials, plus the properties, and the properties basically means, how many electrons, how many protons, how are they aligned, that kind of stuff also is part of electromagnetic theory. So I hope that gives you a bit of a difference between circuit theory and electromagnetic theory. And lastly, it's also said that the study of electromagnetic fields and waves is what we'll be studying in this course, electromagnetic theory. Okay. All right, moving on to slide number 4. This is a quick summary of this whole section 1-2. And this section is called Dimensions, Units and Notation. I'm not going too deeply into this because I think everything here you probably have seen already. This fundamental SI units, length, mass, electric charge, temperature, we've seen it before. Prefixes and magnitudes. Well, I guess we haven't seen exa, peta, but we certainly know mega, kilo, giga, milli, micro, nano, pico, femto. All these we have seen before when we have done EE 188 or EE 280. So hopefully you remember some of this. And then this last section here on the right side is probably, most of it may be familiar to you, but we should also see how in this textbook, in this course, anything that's different from what we have learned? If so, we should become aware of it. So for scalar quantities, he uses this notation where, for example, C for capacitance, right, is written like this. Units are written as like this. For example, volts per meter. Vector quantities is used a lot in the textbook, and it's written in bold. That means, see this E, it's in bold font. So he calls that boldface Roman for an electric field vector. Unit vectors, and what is a unit vector? We'll learn that shortly. But for a unit vector, he uses a small letter and a small hat. He calls that the circumflex over the letter. And it's also bold. Lastly, phasors. And we have studied phasors, so it should not be new to you. A phasor has a little tilde on the top. And a phasor, in this case, he's shown, can be a time-varying scalar, like ET can be written with a tilde without bold. So this is the phasor counterpart of the sinusoidally time-varying scalar field, while E with a bold is the phasor counterpart of the sinusoidally time-varying vector field, right? So there's a slight difference here between how we have thought about phasors in the past. We have always thought that they are just always bold and they have a magnitude and a direction. But here he's talking about even a scalar part of a field, of a quantity, can be a phasor, and when it's bolded, it is the phasor counterpart of a vector field. So scalar field, vector field, right? Both can have a phasor component, is what he is mentioning. So let's see how this maybe affects us later on. But for now, I'm going to just leave it at this and say that this is how it's shown in the textbook. Okay. With that, we move on to the next topic. And there's three topics here. Let me go back quickly. So the three that we're going to cover, one we have covered, 1, 2. 1, 3 is the nature of electromagnetism. And then there's something important called traveling waves. So we are moving on to 1, 3 here on slide 5. And of this, there are again three important topics. Well, there's 4. There's gravitational force, electric fields, magnetic fields, and static and dynamic fields. Gravitational force, I'm going to skip. Please read it yourself. I'm sure you know most of it. But we're going to zoom into 1, 3, 2 electric fields and then followed by these two other. Okay. Now, all these topics, this is kind of an introduction, right? Chapter 1. Each of these materials, or each of these topics, we're going to cover in a lot of detail. So what he has given here in chapter 1 is a brief introduction without going into too much detail. And secondly, a lot of this should be familiar to most of you from high school physics. Having said that, of course, there's some new stuff that will keep coming in. But chapter 1, again, I think we don't go into too much depth. That's all I wanted to say. But we will cover some topics that you're supposed to remember in the back of your mind as you go through the course. All right. So let's start with electric fields. And here are some of the topics that were introduced in the chapter in the textbook. Everything that I'm showing here, most of it is going to be from the textbook. And many of the figures, etc., I'm just copied and pasted so you can see them here. And hopefully you have your textbook and you can follow along and read the chapter so you get more of the material, more of the background. I'm just highlighting the important stuff. Important from two perspectives. One, of course, you want to understand the subject and understand the key findings, the key results, the key ideas. But more important, prepare you to solve problems, right? That's my job. If you love the subject and you want to know more and more, there's lots of resources. Our textbook, plenty of other resources online, other textbooks, you can keep reading those. But I will cover almost everything from the textbook with a view that we have to be able to solve problems in quizzes and exams. Okay? All right. So having said that, the idea of a single electron and charge, right? So charge in coulombs due to a single electron is E equals 1.6 into 10 to the power minus 19 coulombs. You've seen this before. And the charge of a single electron, correctly speaking, should have a minus sign, minus E. The proton has the same charge, but it has a plus sign. Now the electric field intensity, E, due to any charge Q at a distance r is given by this formula. This figure is actually trying to tell you what this formula is all about. So if you have a charge Q, we know that electric field, these lines are also actually called flux. These flux together give us a field. So these lines, they come out in this direction. And here we introduce a new concept called the radial unit vector. So this R is a radial unit vector. A unit vector always has a magnitude of 1, right? Unity in mathematics means 1. So any vector of whatever magnitude can always be shown as the product of two things. First, you take this unit vector to show what direction it's in. To that you attach or multiply a quantity, a scalar quantity, that's the magnitude. So if you had a electric intensity or field intensity of 10 here, and that's a vector quantity, then you write it as 10 r hat. That means it's 10 and the direction is in this direction as shown by the radial unit vector. So that's the way to write this. We'll do a lot more actually on vectors and representation and vector algebra and vector calculus in the rest of the course. But here we just introduced the idea of the unit vector. So electric field intensity due to any charge Q is written as E equals the unit vector, and then there is a term, a magnitude, which is given by this formula Q, which is the value of the strength of this in coulombs, divided by 4 pi epsilon 0 r square. R is the distance from here to the point under consideration, and epsilon 0 is a universal constant called the electrical permittivity of free space, and this has this value. Okay, I hope you have seen this formula or something like this in the past, but this is an important formula for our course, and that's why it has appeared here. Okay, all right, moving on to slide 7. I just wanted to get a quick example. I found this somewhere else and I brought it in, hoping that you'll benefit from this. Normally I like to do examples and problems in a different recording or come back after the theory is over, but here, because this is not from our textbook and it's easy, just quickly look at it. So the example says, what is the electric intensity at a distance 1 micrometer from a single electron located at the origin in free space? So single electron. So here we show an isolated negative charge and its field and a positive charge and its field, and you'll notice that if the charge is negative, you should actually show it in this direction, the arrows coming in. but the unit radial unit vector, that's still showing in that direction, because the unit vector always shows you the direction of increasing r, and we know radius increases in this direction, right? So that's why that's the direction of the radial unit vector. But let's see how we solve the problem and we learn something from it. So this formula you have seen, and this is in free space, by the way. It's not in water or plastic or any material or steel, but it's in air, free space. So if you use this formula, now for Q, which is just one electron, right? So the charge is with a minus sign. And then epsilon 0, we know is 8.85 into 10 to the power minus 12. Our radius is given as 1 micrometer. So that's 1 into 10 power minus 6 meters square. So you get a value with a negative sign of 1440 volts. And see the right way to write this E, because E is a vector, you must show the unit vector to show the direction, and then you must show the magnitude. Okay? So I want you to understand this is how the rest of the textbook will show many values that we calculate and we use. And you clearly have to know how to follow this system, this method. That's why I brought this example to teach you, the importance of the unit vector, writing the plus, minus, etc. Okay? So this is the solution to the problem. Now you may be surprised, right? You're thinking one little electron is giving me what? 1440 volts. That's a lot of volt, right? That you touch that, you could get killed. So such a strong field exists near an electron at a distance of 1 micrometer? It's a good question. How come we are not getting killed when we touch, basic steel or copper? I'll leave you to think about that. It's an interesting question I found somewhere. I know the answer, but I'm sure you'll find it out also. But apparently an electron can create a strong field like this. Okay? All right. I'm going to move on. Some more definitions, all still related to electric fields. So, now I mentioned free space, right? Previously, we had a formula with epsilon 0 for free space. But what if we are not in free space and we are in some material? Let's call it steel, right? We want to find out how electric current or charge, electric field exists in steel or it exists in copper, etc. So for a different material other than free space, the epsilon 0 in the denominator is changed to epsilon, which is the product of two terms, epsilon r and epsilon 0. Okay? And epsilon r is a dimensionless quantity called the relative permittivity or dielectric constant of the material. For vacuum, epsilon r is 1, so we just use epsilon 0. Air also is close to 1, so air and vacuum are pretty much 1. Other materials, epsilon r is different. For metals like copper and steel, ER is very high, infinity almost. For other material like non-conductors, insulators and silicon also, here's the value. Now you can look up these values, but the important thing is to remember that in some media, some material, the formula changes to put an epsilon here and not the epsilon 0. One other quantity or idea you need to become familiar with is electric flux. So electric flux phi E is all the electric lines of force emanating from a charged body. So all these lines of force together, it's called electric flux. Now these are all imaginary lines. I don't think there's really any lines like this inside any metal. But this is how we model it, right? This is how we think of it in physics and engineering so that we can proceed to use the material and the ideas we learn here. Now, an associated quantity is electric field density, which is coulombs per meter square, and its formula depends on this E. So if you take this formula, take out the epsilon, basically whatever is left is D, and D is something called electric flux density. Okay. All right. I'm not going to spend too much time. These are still definitions. So I'm going to skip through, at high speed. Now, one other topic that we've been introduced to is the force. So if you have a charge like this, and you have another charge, now this charge creates a field, right? An electric field E. Now if you put another charge Q1, maybe I should put that somewhere here, or Q prime, then that Q prime will feel a force, it will experience a force called Fe, which is the product of the charge value and E. So this is another important formula to remember for force. Then if you have two charges, both existing, at a certain distance from each other, then we can say that the electric force acting on one charge, say Q2 due to charge Q1, is written like this, and vice versa. But here both the Q1 and Q2 appear in the formula as the product, and the R appears as an R square, and the rest of the formula you can see. This is also a vector, it has a direction. Okay. So this is another method or formula, set of formulas we see in the textbook. A little more here, electric fields. The law of conservation of electric charge states that electric charge can be neither created nor destroyed. I'm sure you've seen this before. Similarly, the principle of linear superposition states that if there are two electric charges, then the total sum of the field is the vector sum of the fields of the individual due to the individual charges, right? I'm sure you remember from circuit theory the idea of superposition. The same thing applies to fields also. So one other thing we have to learn, and then we are done with electric fields, is the idea of dipoles. So from this drawing you'll see that if there is one electric charge, an isolated charge which is a positive in this case, and it's introduced into a whole bunch of other neutral atoms, then each atom now becomes what's called an electric dipole. That means its plus and minus, which previously was in neutral form, now become polarized. That means the protons, the positive charge moves to the end away from this charge, and the negative charges move towards this charge. And this process is called polarizations. Okay? All right. Similarly, we now look at magnetic fields. That's the next topic, 133. Now again, drawings like this, magnetic field, I'm sure you have seen this. I don't want to spend too much time on this. One important factor is that magnetic poles, the north and south, always exist in pairs, right? You cannot have only one. All right, moving on to slide 13. This is one of the properties that's been introduced in this chapter, so I'm just repeating it for you. This is obviously not everything about magnetism. We're going to spend many weeks on this, but this is an introductory ideas. These are introductory ideas, so you should pay attention. So what this says is, if there is a current flowing in a conductor in the z axis, then the magnetic field created is shown in this direction, and the formula for the magnetic field, which is a vector, a magnetic field density B, or flux per unit area in Teslas, is given by this. Here we have a new quantity called mu 0, and that's the magnetic permeability of free space. Similarly, if you want to find the magnetic field density in some material, not just free space, not in air, then you now have this relationship mu equals mu r mu 0, similar to what we saw in electrical fields, and mu r is another dimensionless quantity. For steel, mu r is 5000, otherwise generally it's considered 1 for most materials. So you use, instead of mu 0 here, you use mu in the formula. One other topic, magnetic field intensity H. It's related to B, which is magnetic flux density, by B equals mu H. So pay some attention to this, understand what this phi unit vector means compared to the x we saw previously, and why it's being used here. Another thing is force. Similar to what we saw for electric fields, if a charge Q is somewhere in this neighborhood, then the force experience, the magnetic force experience, is given by this formula. Another important factor that connects mu 0 and epsilon 0 is C. Isn't this surprising? C is the velocity of light in free space, and this formula is important. We'll use it later in problems. Okay, now we come to static and dynamic fields. When electric and magnetic, when time is brought into the picture, right? Varying time. How do electric and magnetic quantities vary with time? So that's something we'll study in static and dynamic fields. And what is static and what is dynamic, what is periodic, what is sinusoidal? I'm sure you know all these by now, but it's a summary is available in the textbook, and I brought it here. I'm not going to read this, please do it yourself. So the three main branches of electromagnetics are electrostatics, magnetostatics, and dynamics, where things are varying with time. So the partial derivative of time, if it is 0, then it's steady charge, stationary charges. If currents are steady, that means DC, then we call it magnetostatics. When everything is varying, then we call it electrodynamics. And the quantities that we just introduced, they're all shown here. Okay. So this is something that we'll be studying. These next 5 chapters are all about this in the textbook. But here is a summary of the definition of each one of these branches. Here's the same epsilon 0, mu 0. A new item called conductivity. Well, it's not really new, it's Siemens per meter. That's also something we'll look at in detail. Okay? Alright, I've come to a very important topic that we need to spend a little time understanding. That's why I rushed through it a little bit. Traveling waves, and this is section 4. And here we have 2 topics, 4.1 and 4.2, lossless, lossy. Lossless means a pure vacuum where no friction and no other material exists to slow down electromagnetic waves. That is no loss. Lossy means real material where nothing can go on at the same amplitude forever, slowly it dies. So 2 cases. Okay. So what is a traveling wave, right? Waves on the surface of a lake, sound waves that travel through air. mechanical waves on strings, electromagnetic waves like microwaves, light, X-rays, all these are waves. Properties. Waves can be transient or temporary, or waves can be continuous. Transient is you throw one stone slowly into a lake, the waves appear and then they disappear. But let's say you have a machine that's continuously rotating, like an alternating machine, a generator. The waves that it creates are continuous, they go on forever, right? So that's the difference between temporary and continuous. Waves carry energy, waves have velocity or speed. Waves also have the property of linearity, which means they satisfy superposition. Okay? So those are some of the properties. So here's some pictures to show you traveling waves. Here's when you just pull a string once, how it travels. Here's when you clap, how that pressure travels in air. Okay? I'm sure this is not new to you, so I hope I don't have to spend too much time. Here's a graphic from our textbook that talks about two-dimensional, three-dimensional. Two-dimensional wave in a lake, then plane wavefront creates cylindrical wave and spherical waves. These are three-dimensional. Okay. Finally, we come to some mathematics. And the mathematics here will not be totally new to you, I hope by now, because we did E188 and E280. But there is a slight modification to what we studied, which you have to become very familiar with. So previously when we studied sinusoids, we only have a function of time, right? And we only had this portion, am cos omega t with a phase. Now we talk about two different independent factors, not just x, but x and t. Not just t, but x and t. And then the dependent is, of course, y. So the formula, the general form is now am, the amplitude, cos omega t minus beta x, which is a factor related to length. And that is brought into the sinusoid. And then you can say the amplitude y in this direction is a function of two factors, one time and one length. Now this section on angular frequency and time period, I won't go too much into it, but you must now pay attention to spatial frequency and spatial wavelength, beta, radians per meter, and lambda is spatial wavelength in meters. So you can see lambda, and both exist at the same time. Time on one axis, wavelength on the same axis, together is what you have to visualize. Okay? And then there is a phi, which is the phase angle, which is still important. But now slowly start becoming familiar with this. Now some of these slides I got from somewhere else. This is not from the textbook, but I thought this is an easy introduction to the topic, and then we look at the material from the chapter from our textbook. So bear with me for a few minutes. Let me move ahead. Here's a traveling wave. Another important relationship. Now look, at the previous page we saw some relationships. 2 pi, what is lambda? Lambda equals 2 pi by beta, similar to t equals 2 pi by omega. Now moving on, there's something called phase velocity or wave velocity, and that's given as Vp as a product of lambda and f or the ratio of omega by beta. Another useful relationship helps us when the wave is light. Remember, light is also electromagnetic radiation, right? So a light wave travels at a speed of c, and that is 3 into 10 to the power 8. Similarly, cs is the speed of sound, which is 343 meters per second. Both these also satisfy this relationship, which actually comes from this relationship, right? So remember this, because you're going to use all these quite a lot. Now, one other thing I want to show is wave traveling to the right, which is this, and wave traveling to the left, which is this. Actually, this and this are connected. Okay? Okay. I'll stop after this example. Again, I have a few more slides on this section, sinusoidal waves. I will stop and then cover it up in the next recording, and we'll also do some problems. But give me 1 minute to finish this. The simple example, if you have this waveform and this is a sound wave, the frequency is given as 440 Hertz, which is a good sound, you can hear it. There's no phase angle, it's 0. And CS is given. Find these quantities, omega, beta, and lambda. So omega you know already, 2 pi f. We have used the formula many times in previous courses. So 440 Hertz becomes 2764 radians per second. Beta is omega by velocity. So that's roughly 8 radians per minute, per meter. And lambda is 2 pi by beta, which is in the previous formula here, right? Or it's here. Lambda is 2 pi by beta. So that is 0.773 meters. So this 440 Hertz frequency in air converts to a lambda of 0.773 meters, that's the wavelength, and it has an angular frequency of 2764 and the spatial frequency of 8 radians. So a simple introduction to the actual numbers involved here. So please take a moment to understand and digest this, because stuff like this becomes important as we start to solve problems. Okay, so 2 minutes over. Let me pause here and come back in a new recording.